Hello everybody, my name is Professor Soborno in Bari, and today we're going to be looking at some more physics. So today we're at physics 126. I won't be able to do that factorial guy anytime soon. So today we're going to be looking at the kinetic energy of a pion. So a pion regularly has about 2.4 times 10 to the negative 28 kilos of mass, I would think. And I believe that its average speed would rank around 2.4 times 10 to the 8 meters per second. But before that, I want to talk about space-time and how space intertwines with time. Say you see a lady on a very, very fast train eating a meal. For her, it takes 15 minutes to eat the meal. So, when she's on a very fast train, moving at say 0.65%, 0.65 c, so, or 65% the speed of light, and let's say she's in her seat and she's sitting down to eat a meal, because her destination is very far away, even in cosmic terms. So, she sits down to eat a meal. Now, for her, it takes 15 minutes to eat the meal. But for an outside observer, would say, an outside observer observing the train at rest would say it would take 20 minutes. Now, as we know, this is the effect of time dilation. So, time gets longer as your speed gets higher. But let's say that she's eating on a very fine marble plate that doesn't contain lead, by the way. We don't want her to be poisoned. Anyways, however, let's say that this plate of hers would be 20 centimeters. To us, we would see it as 15 centimeters. So, as velocity goes up, time also goes up. But somehow, length goes down due to length contraction. So, does that mean that time and space are intertwined? Certainly, because as time is dilated, length contracts. So the two kind of balance themselves out. So, even though it takes it's a smaller plate, it takes longer to finish, which is a very weird concept, because we normally regularly think about it as if there's a larger plate, it takes, here it's a larger plate and it kind of takes shorter to finish. It's kind of weird because we know all the perspectives are right, not just the one of the lady on the super train or the man standing at rest. So, now, we don't observe this because normally the train would just go past us in a vision where we couldn't even detect it with our most delicate machines. So, that means, that's the only reason why we can't detect these changes in the everyday world when they're traveling this ridiculously fast. But when we can track them down, we can observe huge changes. Like in the microscopic world of the pion, we can easily track down where it goes. So, let's see how what the kinetic energy of this is. So, we learned that kinetic energy must be equal to, so K is equal to, this is an important equation, gamma m naught c minus, squared, minus m naught c squared. And as I said in the last lecture, you might notice this is being the total energy minus the rest energy. I should probably just write the subscript in purple.
Use only one color.
Can I use two? Okay, so now this is the concept of space-time being intertwined. And I think you'll understand it better from that small analogy, right? Okay.
Purple one, put it down.
So I'm going to use this one later, and okay. So let's say that we have these values for a pion. Now let's plug them in to this equation. Gamma m naught c squared minus m naught c squared. Now, this is actually surprisingly easy. Gamma can be calculated, as we know, like this. Now, this would be equal to 1 over the square root of 1 minus v over c squared is going to be 2.4 times 10 to the 8th power over 3 times 10 to the 8th power whole squared. We can cancel these out. 2.4 over 3 is 0.8. Squaring that will give you 0.64. Now, you'll see how this works out. Because 1 minus 0.64 is 0.036, and the square root of 0.36 is equal to, you guessed it, 0.6. So now, that means that we get something like this, I believe. So that's 1 over 0.6 is 5/3. So now that's one part of the equation. We know our rest mass, which is equal to 2.4 times 10 to the negative 28th power, and our speed of light is going to be equal to 9 times 10 to the 16th power since we squared it. And then we have this minus and this other gag. So 2.4 times 10 to the negative 28 times 9 times 10 to the 16th power. So another way we can rearrange this is basically this gamma minus 1 times m naught c squared. But we're not going to do that. Oh god. So 5/3 to 9 will give us 15. 15 times 10 to the 16th power times 2.4 times 10 to the negative 28th power. That changes this into that I believe 36 times 10 to the negative 28 plus 16th power. So that changes to this. This changes to this, I believe. So 36 times 10 to the negative 12. That becomes 11 as we put this dot here. So then we subtract this from this other thing. 2.4 times 9 is going to be equal to, so this is 18. And then this is 30. Okay, so that's going to be equal to 21.6, I believe, times 10 to the negative 28 minus 16. Now this plus 16. Now this is going to be equal to 12. Then putting this dot here, we're going to estimate this to 2.2. It becomes 11. Now we can just subtract, since these are common terms, which gives us 1.4 times 10 to the negative 11th power. Please don't tell me that's legal math. Okay, so now we found the kinetic energy of this pion moving in nearly the speed of light. It's so small, it's really, really small, in fact. For reference, I believe that, okay, I think the jewel was based on something too ridiculous for you to understand. So yeah, that wouldn't really fit the theme of this. Anyways, thank you everybody for watching, and I'll see you next time.